Welcome back to Applied Mathematics. In this video, I want to go through a couple of classifications of application problems called percent problems and mixture problems. The ideas here are not that closely related to each other, but they all fall under the general umbrella of we want to write an equation, but there is some hidden information about what's going on that is necessary in order to do so. You should be familiar with percent problems already, so we'll go through those fairly quickly. Percents are often used in mixture problems, so that's going to be a nice review before we get into what should be new material for most of you. All right, let me get my head out of the way and let's start in with a basic percent problem. 37 is 53% of what number? There's not a whole lot going on here. The number 37 is the number 37. Is, just like any other verb, is going to be an equal sign. The one trick in this problem, 53% looks like it is a number, but percents are not numbers. You need to rewrite 53% as a number. That can either be a fraction, 53 over 100, or a decimal, which is my preference, 0.53. The word of almost always means multiplication. What number? I have no idea. I'll call it x. Solve for x by dividing both sides of the equation by 0.53. My calculator is happy to tell me that 37 divided by 0.53 is 69.81132, etc., etc., etc. But I've got two significant digits going on here, so I'll round to two significant digits and call it 70. I'll put a decimal point to make sure that that 0 reads as a significant 0. So 37 is 53% of 70. There we have it. That's all we needed here. On to the interesting things. What is 60 increased by 20%? This feels like it's going to be a really easy problem. What? I don't know. Let's call it x. Is equal sign. 60. 60. Increased by, add, 20%, 0.20. But that's not the end of the story. The reason that percent problems are difficult is because a percent always has to be taken of something. A percent is not a number by itself. You can't just add 0.20 and call it increasing by 20%. You have to take the percent of the thing you're increasing, which in this case is 60. All right, from here I can use a calculator. 60 plus 0.2 times 60. My calculator tells me is 72. Here's where things get interesting. We tend to think of the words increase and decrease as being opposite of each other, but when it comes to working with percents, it doesn't work that way. If we start at 60 and increase by 20%, we end up at 72. Well, what if we start at 72 and try to decrease by 20%? Well, our setup is still mostly the same. X equals 72. Decreased by means subtract. 20% is still 0.20. It's still got to be a percent of something. And the thing we're decreasing is 72. So we just repeat the 72 right there. Then we grab out our calculator. And my calculator tells me that this is 57.6. Since I've only got two significant digits going on here, I guess I'll round that and call it 58. But definitely not 60. And that can be a problem. Because what if we wanted to end up at 60? $60 is what number decreased by 20%? Right? So now we're switching things around. We know we want to end up at 60. We don't know where we're starting, so we put the x here. We subtract because it's decreased by, we write 20% as a decimal, 0.20, and then we multiply by the thing we're decreasing, which is x. So we have 60 equals x minus 0.20x. That's different. We have the tools to solve this. It's not that bad, but you have to take the time to go through it and not panic. If it helps, remember that a variable by itself you can think of as having a coefficient of 1. And that coefficient of 1 is an exact value. So you can put a decimal point and you can put a couple of zeros after it, and it's still the same number. But doing that sometimes makes it a little bit more clear. When we're subtracting here, x minus 0.20x is going to be 0.80x. Get x by itself by dividing both sides of the equation by 0.8. And my calculator is happy to tell me that 60 divided by 0.8 is 75. All right. For the sake of brevity, I've stuck at very abstract problems here. I didn't dive into any of the applications of this because I really wanted to focus on the terminology, right? Increased by, decreased by, thinking about where you're starting and thinking about where you're ending. So thinking about those ideas and thinking about how to set up the equation is the important thing. I can throw in a ton of extra terminology in here, right? Jim's current salary is $55,326.48. He's earning this after having received a 3% cost of living raise last year. What was his salary last year? Well, this year's salary is last year's salary increased by 3%. You can plug in some numbers and you can try to solve from there. If you are careful about it, you will realize it's going to take a form similar to this with the variables on the right-hand side and some algebra needed in order to solve it. We'll have plenty of time to practice those, but for now I just wanted to remind you of the basic ideas. Instead, let's turn our attention to the other topic of this video, mixture problems. For an industrial application, you need 10.0 liters of, let's get some more significant digits here. Let's call this a 5.0% hydrochloric acid solution. You have 30.0% hydrochloric acid in the stockroom, as well as pure water, distilled water. How much of each should you mix together to get your 5% solution? All right. So, to organize this, what I realize is that I have the same pieces of information about a couple of different objects. In this particular case, those objects are the reagents. Each one has a volume and a concentration. The 5% hydrochloric acid solution has a volume of 10.0 liters and a concentration of 5.0%. I'm going to write that as a decimal, 0.050, because that's going to make my life easier a little bit later. I know that that reagent is what I want at the end of the day. I've got a couple of other reagents that I'm going to mix together. I have a 30% solution. I don't know what the volume of it is, but I do know it has a 30% concentration. As a decimal, that's 0.300. And then I know I have some water. Pure water has no hydrochloric acid. The concentration we can write as 0 if we so desire. All right. We are asked about the amount of the 30% solution and the amount of water we're going to use. If I'm creative about this, right, you could just throw in two variables, call one x, call the other one y, and technically it would work. But if I'm creative about this, I might realize that, well, however much of the 30% solution I use, let's call it x, I know that I need to end up with 10 liters. So subtract off the x of the hydrochloric acid, and that gives me how much water I need to add. The other thing that we need to think about here is, what do we mean by a hydrochloric acid solution? Well, it means we have a bucket of water that has some hydrochloric acid dissolved in it. So we might want to ask the question, how much hydrochloric acid do we have? Well, if we have 10 liters of a 5% solution, 5% of 10 liters, multiply those two things together, and we get 0.5 liters. X liters of a 30% solution, 30% of x is, before I get there, I had two significant digits. I should leave that, 0.50. Then I have 0.300x liters of hydrochloric acid in my x liters of a 30% solution. And the pure water, because it has no hydrochloric acid in it, it has no hydrochloric acid in it. This last column is the key to it all. Hydrochloric acid can't come out of nowhere. So the amount of hydrochloric acid we pour into our mixture, 0 plus 0.300x, has to be equal to the amount of hydrochloric acid in the final result, 0.50. So I grab my calculator, I divide 0.50 divided by 0.300, and I get 1. I guess I only have two significant digits, so I'll round that to 1.7. And I know that X was the volume of the 30% solution. And I know that the rest of the 10 liters had to be water, so 10 minus 1.7 is 8.3 liters of water. And with that, I am able to answer this question. All right. So that's the basic idea of a mixture problem. You're going to have a couple of different things that you're looking at. You're generally going to have two, sometimes three, but generally two things that you're mixing together, and they're going to form some sort of an amalgamation. You generally know how much of each thing you add in, how much of the stuff you have in total, concentration of mass and volume. Whatever you pour in is what you have once you've mixed it together. So whatever that column happens to be, add together your things you're mixing together, and that gives you what you have at the total. Those things all have some sort of a rate to them. In this case, it was a concentration. Sometimes it will be a cost. Sometimes it will be a color saturation. Sometimes it will be, I don't even know what else, but it could be much of anything. And you should realize that if you multiply the amount times whatever property there is, it will give you the amount of that property. And you can realize that if you add those things together, add together what you're putting in, and it gives you what comes out. So trying to break down a problem like this and set things up in a table is a great way of organizing yourself so that you can get a nice equation that you can work with. Once you have that, you can start solving the equation. It gives you what you need to answer the question. All right, that's all I have for you in this video, so I'll wrap up with that. As always, thank you for joining me, and I'll see you in the next one.